Hello, students. Have you ever looked at two very similar molecules and wondered, why on earth do they react so differently? Well, today, we're going to solve this exact puzzle. We are diving into one of the most important topics in organic chemistry, the chemical reactions of haloalkanes.
So let's look at the central question. You take a haloalkane, you do a reaction, and you get an alcohol, okay? But then you change the conditions just a tiny bit, or you take a slightly different molecule, and suddenly, poof, you get an alkene. Now, I know it can seem very confusing, almost random, but trust me, it is not. There are very clear rules, and by the end of this session, you will have a solid framework to predict exactly which path a reaction will follow.
You know, to predict anything, we have to first understand the very heart of the matter. For haloalkanes, all of their reactivity, everything, comes from one single place, that carbon-halogen bond. And the absolute best way to think about this bond is to imagine it as a loaded spring.
So, what is this loaded spring concept? It's really simple. You see, the halogen atom is highly electronegative, right? So it's always pulling the shared electrons in the CX bond towards itself. This makes the carbon atom a little bit electron deficient, giving it a slight positive charge. And that makes it a perfect target for anything electron-rich to come and attack it. And at the same time, the halide ion is very happy to just leave and be on its own. So this tension, this pull, makes the bond just like a compressed spring, ready to snap into action at any moment.
So, here is the most important part. This spring is predictable. The direction it uncoils, whether it will substitute the halogen for something new or eliminate it to form a double bond, is not a game of chance. No. It is decided by two main things. One, the structure of the haloalkane itself. Is it primary, secondary, or tertiary? And two, the specific conditions we choose in the lab, like what is the temperature and what kind of reagent are we using to attack it.
To make this even easier to remember, let's use a very simple but powerful analogy. I want you to imagine that the haloalkane molecule is a fortress that we want to capture. And to capture this fortress, there are three basic strategies that we can use.
So what are our three strategies? First, we have the direct assault. This is a very fast, single-step attack, and in chemistry, we call it the SN2 reaction. Second, there is the siege. This is a much slower, more patient two-step process, which we call the SN1 reaction. And the third strategy is something different altogether. It's not about capturing the fortress, but forcing everyone to abandon it through an escape tunnel, and this we call an elimination reaction.
And this analogy perfectly explains the difference. For a direct assault, the SN2, you need a very strong and agile attacker. That's our strong nucleophile. And it only works well on an open, undefended fortress, which is our primary haloalkane. The attack is one single coordinated move. Now compare that to the siege, the SN1. This is the strategy for a well-defended fortress, like a bulky tertiary haloalkane. Here, the central carbon is crowded, it's shielded by three big alkyl groups, so a direct attack is just not possible. So what does a weaker nucleophile do? It waits. It waits for the guard, our halide ion, to leave on its own. That first step is slow, but once the guard is gone and the fortress is open, the attack is immediate and fast.
All right, so that was the story of the fortress. Now let's leave the battlefield and step into the actual laboratory. How do these strategies actually translate into real chemistry? Well, it's all about controlling the conditions. I want you to picture three different lab benches in your mind.
On our first bench, the SN2 lab, we choose a primary haloalkane and a strong nucleophile, like hydroxide. The reaction will be a quick, direct substitution. Then we move to the SN1 lab. Here, we take a tertiary haloalkane and a weak nucleophile, like water. In this case, the halide ion leaves by itself first, forming a stable carbocation intermediate, which is then quickly captured. And on our third bench, the elimination lab, we change the game completely. We use a strong base and we increase the temperature. These conditions heavily favor the escape tunnel route, and instead of substitution, we form an alkene.
Now, theory is one thing, but seeing it happen makes it so much more real. So let's look at a very common experiment that you might even do in your own school lab, one that perfectly shows the direct assault or SN2 pathway. Let us see how to make an alcohol.
So how do we do it? First, we take 1 bromobutane. It's a colorless, oily liquid, and most importantly, it's a primary haloalkane, our open fortress. Then, we mix it with an aqueous solution of KOH. The hydroxide ion here is our strong attacker, our strong nucleophile.
We just heat the mixture gently, maybe in a warm water bath, to keep the temperature steady. And as the reaction happens, you will actually see the oily layer of 1-bromobutane vanish as it gets converted into 1-butanol, which dissolves in the water. It's a perfect textbook example of an SN2 reaction.
Okay, so we've moved through this topic quite quickly. Let's just pause for a moment and put everything together into a few simple takeaways. I want you to think of this as your master key for unlocking any question on this topic. So, what are the 3 things you must remember? First, the core idea. That carbon-halogen bond is a loaded spring, always ready to react. Second, that mental picture of the fortress. Always ask yourself, are the conditions right for a direct assault, SN2, a slow siege, SN1, or are we forcing an escape, elimination? And third, keep that real lab example in your mind. Making 1-butanol from 1-bromobutane is the perfect direct assault SN2 reaction.
So, my final thought for you is this. If you can truly master these 3 simple ideas, the idea of the loaded spring, the story of the fortress, and that real-world example of making an alcohol, if you can hold these 3 points clearly in your mind, I promise you, predicting the outcomes of these reactions will become a much, much lighter and more manageable task for your studies and especially for your exams. All the very best.